If you've ever walked past a parked aircraft and looked into the engine, you've seen it, a white spiral painted on the center hub of the fan. Sometimes it's a simple swirl, sometimes it's a more complex pattern, but it's there on almost every commercial jet engine. Most passengers assume it's decorative, a logo perhaps, or just some kind of manufacturer branding. It looks too simple to be important. It's not decorative. That spiral is a safety feature, and it exists because jet engines are extremely good at killing people who can't tell if they're running. This is the story of why a simple painted pattern saves lives on airport ramps around the world. To understand why the spiral matters, you need to understand the operating environment of an airport ramp. When an aircraft is parked at a gate, the area around it becomes a workspace. Ground crews move constantly around the aircraft. Baggage handlers load and unload cargo holds. Fuelers connect hoses to wing tanks. Caterers stock the galleys. Cleaners enter through service doors. All of this happens while the aircraft is being serviced, often with engines running or in various states of operation. Now here's the danger. A jet engine doesn't look dramatically different when it's running at idle versus when it's completely shut down. At full power, yes, the sound is unmistakable. The heat shimmer behind the engine is visible. The sheer violence of the exhaust is obvious, but at idle, the engine is turning, but relatively quietly. The fan is spinning, but smoothly. To someone working nearby, focused on their task, the difference between an idling engine and a stopped engine might not be immediately apparent, and that difference can be fatal. A modern turbofan engine at idle is rotating the fan at roughly 400 to 600 revolutions per minute. The fan blades are moving at about 200 kilometers per hour at their tips. The air being drawn into the intake creates a vortex that can pull loose objects and people toward the engine. The ingestion danger zone around an operating engine extends several meters in front of the intake. Anyone standing too close can be pulled in, and what happens next is exactly what you'd expect when a human body meets spinning titanium blades. This isn't theoretical. It has happened multiple times. Ground crew fatalities from engine ingestion are documented throughout aviation history. In most cases, the victims simply didn't realize the engine was running. They walked too close to what they thought was a shutdown engine. The intake vortex did the rest. The spiral exists to make engine rotation visible from a distance. When the engine is running, even at idle, the spiral creates a visual effect. The rotation blurs the spiral pattern into a distinctive disc or creates a hypnotic swirling appearance depending on the design. This visual is clearly different from a stationary spiral. From 20 or 30 meters away, a ground crew member can glance at the engine and immediately know that engine is running. Stay away from the intake. At night, the spiral is typically painted in white or reflective paint so that any available light catches it and makes the rotation visible. It's a remarkably simple solution. Paint. Just paint. But it provides an immediate intuitive visual warning that requires no training to interpret. Spinning equals danger. Static equals safe. Let me walk you through the physics of why engine ingestion is so dangerous. A turbofan engine generates thrust by accelerating air. At the intake, it's pulling air in from the surrounding environment. At idle, a large engine might be moving 200 to 300 kilograms of air per second through its core. That airflow creates a pressure gradient. The pressure right at the intake is lower than the ambient pressure further away. This pressure difference is what creates the ingestion vortex. The danger zone isn't directly in front of the engine. It's actually slightly to the sides and below, where the vortex tends to form. The vortex can extend 2 to 3 meters from the intake under certain conditions. If you're within this zone, you're not just being blown by air, you're being pulled. The suction is significant enough to destabilize a person, especially if they're crouching or bending while working. Once you lose your footing near an operating intake, recovery is extremely difficult. The flow accelerates as you get closer. What started as a strong pull becomes overwhelming force within the last meter. The fan blades are rotating fast enough that they'll dismember a human body instantly. Engine damage is severe. The engine typically requires complete overhaul or replacement. But that's irrelevant compared to the human cost. The spiral won't prevent someone who deliberately ignores safety protocols, but it provides a constant visual reminder that the engine is alive. Every glance at the engine reinforces the message. This one is running. This one is not. Different engines use different spiral designs, and there's actually some engineering behind which pattern works best. The simplest design is a single spiral line starting at the center and curving outward. When rotating, this creates an apparent swirling motion that's easily recognized. Some engines use a comma shape or a curved teardrop. This creates a distinctive off-center rotating appearance. Others use multiple spiral arms, similar to a pinwheel. These create a more complex rotating pattern that some argue is more visible in peripheral vision. There's been research into which designs are most effective at various distances, lighting conditions, and rotation speeds. The optimal design depends on the specific engine's fan diameter, typical idle speed, and operating environment. General Electric, Rolls-Royce, Pratt & Whitney, and CFM International all use slightly different spiral designs on their engines. Airlines sometimes have preferences for specific patterns, but all of them serve the same fundamental purpose. Some modern aircraft use additional visual indicators beyond the spiral. Newer engine cowlings may include LED warning lights that illuminate when the engine is running. These provide a secondary indication that doesn't rely on ambient lighting. Some engines have painted markers on the fan blade tips that create a distinctive pattern when rotating. This supplements the center spiral with motion visible at the blade periphery. Ground crews also receive extensive training on engine danger zones. They're taught to always approach aircraft from specific angles, to never walk in front of engines without positive confirmation they're shut down, and to treat any engine as potentially running until verified otherwise. But training has limits. People get tired, distracted, or complacent. The spiral provides a passive safety layer that works regardless of mental state. It's always there, always visible, requiring no active decision to check. This philosophy of passive safety is common in aviation. Wherever possible, systems are designed so that the safe state is obvious and the dangerous state is visible. The spiral is a perfect example. There's another aspect of the spiral that's worth understanding. It helps maintenance personnel too. When inspecting an engine, technicians need to rotate the fan manually to examine all the blades. This is called a borescope inspection, or a blade-by-blade visual check. The spiral provides a reference point. By watching the spiral as they rotate the fan, technicians can track how far they've turned it. One complete rotation of the spiral means all blades have been examined. Without the spiral, keeping track of rotation during inspection would require marking a blade or using some other reference. The spiral provides this function for free. Let me address a common question. Can the spiral pattern affect engine performance? The answer is not in any meaningful way. The spiral is painted on the spinner, the cone-shaped hub at the center of the fan. The spinner's primary function is to smoothly direct incoming air outward toward the fan blades. It's shaped to minimize aerodynamic disturbance. Paint adds negligible mass and doesn't change the spinner's shape. The aerodynamic effect of a painted spiral versus an unpainted spinner is immeasurable in actual operation. Some high-performance military engines don't have spirals because their operating environment is different. Fighter jets aren't serviced by ground crews walking around idling engines. They're serviced in controlled environments with different safety protocols. But for commercial aviation, where busy ramp operations are constant and ground crew traffic near aircraft is unavoidable, the spiral is a universal feature. There's something philosophically interesting about the spiral. Aviation is an industry built on complex technology. Jet engines involve thermodynamics, metallurgy, aerodynamics, and computer control systems of extraordinary sophistication. A modern turbofan is one of the most complex machines humans manufacture, and yet one of the most important safety features on that engine is paint. Simple, ordinary paint, applied in a pattern that any child could understand. This illustrates a broader principle in safety engineering. The best safety features are often the simplest. They work without power, without maintenance, without training. They communicate danger in ways that transcend language and expertise. The spiral doesn't care if you're a veteran aircraft mechanic or a new baggage handler on your first day. It doesn't care if you speak English, Mandarin, or Arabic. It doesn't require batteries or software updates. It just spins when the engine spins. And that's enough. So the next time you're boarding an aircraft and you see that spiral in the engine, you'll know what you're looking at. Not decoration, not branding. A visual warning that has saved countless lives since its introduction. A painted swirl that says, "This engine can kill you, and right now, it might be running." That's not just paint. That's decades of safety thinking, reduced to the simplest possible form. Speaking of engine safety, there's another feature you've probably noticed: those covers that protect engines when the aircraft is parked. They're not just dust shields. They solve a specific problem related to exactly what we've been discussing. I've explained what happens without them in another video.